Section 2.7, page 3. Now let's go ahead and look at example 5. A water tank has a top radius of 2 meters and a height of 4. So it just tells us that it's a water tank, but because in this case we're going to find out that it's a cone, a radius is always related to a circle, and it could be cylindrical, but it would have stated that. So what ends up happening is I've got my circle up here, and from the center out is my radius at 2, and the height of this cone to its base is 4 meters. If water is being pumped into the tank at 2 meters per minute, how fast is the water level rising when the water is 3 meters deep? So we kind of know how much water is in there, but we want to know the water level, but specifically how fast it's raising. Lots of things going on. So in this case, you're actually also given the visual so that you know it's a cone. So let's break down what we're given. Like I said, the visual is a cone, so that's how we know to work with a cone. And because it is being pumped or filled with water, and we talk about the water level, we're referring to the volume of a cone, and the formula is provided here. The question lets us know that the top radius is 2 meters, and so I went ahead and wrote r equals 2, although keep in mind we have an r down here, but just to focus on radius as a measurement. Then it tells us the height is 4 meters, which is the distance of the cone. So I'm using height where, again, we have a height here, but I'm talking about a specific point in time. Next, we have the phrase that the water is being pumped into the tank at 2 cubic meters per minute. So we need to focus on this cubic meters per minute is letting us know it's a derivative. And if the water is represented by volume, then we have the derivative of the volume is 2, and all of these problems we're taking the derivative based on time. So the last piece of information is we want to know how fast the water level is rising. It is going to be a positive answer because it's increasing, but we've got this phrase, when the water is 3 meters deep. When the water is 3 meters deep. So this is the height we want, but be careful because we'd already said that the height was 4, but this is only when the radius is 2, and we'll come back to that in a moment. So as I start off, I know I'm trying to find the rate that the height is changing. So we just declared we're going to go ahead and use the volume function. And so I take the derivative of v, which is 1, but I need to include a dv dt. 1/3 pi is a coefficient, so it stays there. I take the derivative of the radius, and because the radius is changing, I'm going to have dr dt. In a cylinder, it doesn't change, but in a cone, the radius does. And I take the derivative of the height, which is 1, but because I have a height variable, I need dh dt. So I plug in all the values. We stated that the rate the water is changing is 2, and we won't worry about the units. We said that 1/3 pi is a constant or coefficient, so it stays there. We're specifically interested in information we have right now, which is a radius is 2. dr dt we don't have, and it's dh dt, which is what we wanted. Now, in most cases, we've been able to take all the existing information to solve for dr dt, but we don't have a Pythagorean theorem like the previous problems. So I can't go ahead and solve for it the same way, but here's what we can do. We're actually going to rewrite the question. We're going to get rid of all this work we did because we're going to find a better way to solve this problem. We're going to use substitution so that we don't have a radius, we have something else we can work with. So what we're going to do is talk about similar triangles. That if you think about it, I've got this small triangle here with R and H, and I've got this giant triangle here where I know that 4 is the left side and 2 is the top. I wrote the 4 here because I was afraid if I wrote it here it would be too squished or look like the other triangle. So it's not the diagonal that's 4, right? The diagonal is not 4, only this straight side. So my picture could be deceiving. But I'm focused on the fact that each individual triangle has the ratio of height to radius. And you could have flipped these over and done radius over height, but the key is that you're consistent. I have an unknown triangle and I have another triangle where the values are 4 and 2. These were given in the question. So when I have similar triangles, I can set them equal to each other. I can then cross multiply the 4 and the R. I can cross multiply the 2 and the H. And now I have an equation where I can solve for R. So I'm going to take that equation up here, divide both sides by 4 so that I end up with R equals 1/2 the height, which will be true at any point in this particular triangle, or sorry, cone. So I'm going to go back to my original function, and instead of using R, we're going to use the fact that R is 1/2 the height. But don't forget, R was squared, so 1/2 the height needs to be squared, giving me 1/4 h squared. A lot of people accidentally just put 1/2 h squared, but the 1/2 also needed to be squared. Okay, so let's go ahead and scoot that over here so that I've got my two fractions together. And it was also times h, so I can go ahead and add those invisible exponents to say I have 3 h's. So multiplying my two fractions, my question, my volume, I don't have any derivatives yet, is 1/12 pi h cubed. So now if I take the derivative of the volume, which is 1, but put a dv dt with that, leave 1/12 pi as a coefficient, and then take the derivative of h cubed, which is 3h squared, but put a dh dt with it because I took the derivative of the h variable about time, I now have an equation I can work with. I've got this 3 and this 12, which can cancel to just give me a 4 in the denominator. We had stated earlier that the volume was 2 cubic, was it cubic meters per minute, so we could put the 2 there. And now I do have something for the height. The question said when the water is 3 meters deep. So that's why we get to put this 3 here, of which the 3 needs to be squared to give me a 9. So my original problem is the 2. I now have 9 pi, and don't forget we had a 4 in our denominator, and the dh dt that I originally wanted. So what's in purple is my simplified equation. Since I'm solving for dh dt, you could multiply both sides by 9 pi over 4, but I find seeing fractions within fractions is confusing. So if you really think about multiplying both sides by the reciprocal so that the 4's cancel, the 9 pi's cancel, and on the right side I'm left with dh dt that I'm solving for, I just need to worry about that reciprocal times 2 on the other side of my equation. And so I've got that 8 over 9 pi. In terms of the units, remember dh, what is h? H represents the height at any point in the cone, and we're talking about height in terms of meters. And how is time being measured? Time is measured in minutes in any point in this problem.